Dear students, I welcome you for today's lecture related to the multiple inputs and multiple output system. Now in this multiple input and multiple output system, and there is another single input and single output system, that is SISO. The systems which involves only one single measured variable and the single manipulated variable. Single measured variable and single manipulated variable. It is called the single input and single output system. Then the systems which have more than one measured and or manipulated variables, they are called multiple inputs and multiple output systems. In that, feed forward, then combination of feedback, feed forward, then cascade, then ratio controller, selective control systems, and split range control systems are there. So today one by one we are going to discuss this. In general, we are knowing that we have discussed maximum related to the feedback control system only. So our control variable is measured. Our control variable C, that is measured, that is the temperature of a reaction vessel, and is compared with the set point, and which generates the error. This generated error is minimized by your controller action. Means you are measuring directly the controlled variable. Controlled variable is measured. Here we are measuring the controlled variable, that is the temperature of the reaction vessel, reaction content, and it is controlled with the help of a steam supply. So only one loop that is incorporated, but here we are measuring the controlled variable. Now next is the feed forward control system. In this case we are not measuring the controlled variable. That is the major difference. In the feedback control system we are measuring the controlled variable. However, in case of a feed forward system, we are not measuring the controlled variable. We are measuring the manipulated variable or the load variable. We are measuring the load variable, then we can detect any changes taking place in such variables. That means this is the load variable, that is the flow rate of a coolant. In case of a CSTR, that is continuous stir tank reactor, the corrective actions, that is based on this coolant flow rate and the coolant temperature. So there is a coolant temperature measurement, that is what is coolant flow rate that is there, and we are measuring the temperature of the inlet fluid which is coming in. We are measuring the temperature of a fluid which is entering. In this case, that is feedback case, we are measuring the temperature of a product which is going out. That means the temperature of the fluid in the reaction vessel. However, in feed forward control, we are measuring the temperature of this feed. इसका टेम्परेचर मेजर कर रहे हैं फीड का. That is the difference. In feed backward we are measuring the final product out temperature, that is what feed backward, and feed forward the feed which is entering in उसका measurement है. That is the major difference. in between the feed forward and the feed backward system. So the corrective action is taken only after the control variable changes, say because of change in the load variable. It is called the reactive action. That is what is observed in case of our feedback systems. Corrective actions कब हो रहे हैं? When the control variable change that is there. We are measuring the load variable, then we can detect any changes taking place in such variable. So load variable in this case is the inlet fluid temperature. So it is immediate action, so that there is almost no effect of such load variable on the control system. So whatever the changes that is observed in case of our inlet temperature of the fluid, the corrective action is already taken based on this inlet temperature. That is called the proactive action. That is called the proactive action. In general case, in our daily life, whenever we are driving our vehicle and we see certain obstacles or certain heavy traffic that is there on the road, so we reduce the speed. That is what? Corrective action. Immediately we are not applying the brakes. First we reduce the speed by observing the traffic on the road, and then let it reduce the speed of a vehicle. Acceleration कम कर देते हैं, so that the speed of the vehicle that is reduced, and if required then we apply the brakes. That is what? A corrective action that has been taken, or you will say this is the feed forward control system. आगे में क्या होने वाला है उसके लिए मेरे को पहले क्या तैयारी करने की है, that is what is a feed forward control system. If one applies this feed forward control system in our life, then he will be succeeded every time. Then what are the advantages of this feed forward control system? That is, acts before the disturbance or the load which affects the control system. Then this is good for slow systems. The systems which are slow, there this controller can work in a very proper way. The next is no closed loop, hence no stability. It is not stable as these systems are not closed loops. So load variables are measured and their instantaneous values are used for this control system. That is what the advantage is. Acts before the load that is going to affect, and it is the instantaneous values which are measured, and based on those instantaneous values the corrective action has been given. That means before the entry, as the fluid changes in the temperature of the fluid that is noted, the corrective action start there itself. Then there are certain disadvantages. All the load variables that must be perfectly known. Here only we are measuring the temperature in this case. Now there can be changes in the flow rate also. If I change the throughput of a system and my reaction system demands more supply of the reactant A, so the flow rate that is not measured in this case, only temperature that is measured. In this case, there you can apply the another loop also for measurement of the flow. That is, all the process parameters must be perfectly known. Then the process parameters must not change with the time. That is one of the limitations of this feed forward control system. So as there is no monitoring of control variable, and hence any change in the control variable C due to the process condition will not be taken care by this feed forward control system. We are not measuring the temperature inside this reactor for this control system. In this case, as in case of our feed backward, कंट्रोल वेरिएबल का टेम्परेचर नहीं मेजर कर रहे अपन, प्रोडक्ट जो आउटलेट जा रहा है उसका टेम्परेचर मेजरमेंट नहीं है in case of our feed forward system, and that was the limitation. Now when you draw a block diagram for this feed forward control system, then there is a process. To this process or the system reactor, this is what is our reactor, we are adding this flow rate, that is what is our load variable. So this is what is our load variable that is shown, and its temperature that is measured. So this temperature measurement that goes or gives the signal to the feed forward control. FFC is nothing but feed forward control system. FC is the feed backward control system. So feed forward control system FFC that gives the signal to the valve. The system itself talks of this FFC, it gives the signal to the control valve. So FFC that gives the signal to the control valve, and this control valve, it is going to a jacket. So the jacket that is shown, the fluid which is going into the jacket, and this jacket that is connected to a reactor system in which both this variable that is entering and the heating variable or the coolant that is there. We are considering this example CSTR, that is for a exothermic reaction. That is what? A coolant that is to be used. We have to take out the heat. So based on this system, our block diagram that is developed. Now, what happens in case of a feed forward and a feedback control system for a CSTR? So it's a combination of the feed backward, a combination of feed backward system and a feed forward system. So in a feed backward system, we are measuring the actual temperature of a controlled variable. So this temperature is measured, then our thermocouple is there for the measurement purpose, then transducer, then comparator and feedback controller, and this controller feedback controller which is going to give a signal to the control valve. This is the feed backward control system. And in case of a feed forward control system, whatever the fluid that is entering in, I am measuring its temperature and giving the signal to a controller. Transducer will be there. So it is going to give the feed forward controller system, and this feed forward controller system is going to a control valve. So now this loop is related to the feed backward system, and this loop that is related to the feed forward system. So both these systems are there, and then a comparator has been provided to take a proper decision from the feed backward loop and from the feed forward loop, and accordingly gives its output to the control valve. Both the time, control valve is the final manipulated variable is there. So I suppose you have understood the difference between the feed backward, feed forward, and combination of feed forward and feed backward system. Now there are cascade control system, and these are the commonly used in our chemical process industries. Now what is there in the cascade control system? It's a feedback control system, maybe too slow in action. Then we are going to use this cascade control systems. Slow response, that is the basic reason. Nowadays we have already talked here that there are limitations. The response is slow because of the overall heat transfer coefficient or scale formation, which takes several minutes to give you the actual values. So this limitation of slow action or slow result oriented systems where the time constants are high, so that the combination of different systems that will be used, that is a coolant is circulated. In this case, this is again a CSTR with an exothermic reaction, so that the coolant I am going to use to remove the temperature, so that my outlet temperature T0 of a reaction vessel will be maintained constant. Because I have to carry out a reaction at a constant temperature, the temperature of a reaction should not shoot up, it should not go out of control. As a result, or there can be a certain side reactions which can degrade my product, or which can give the certain byproducts also if the temperature shoots up. Or in case polymerization reactions, then the degradation that may come. Or in food industries also, the degradation that may come with the increase in the temperature. So this is very necessary to maintain the temperature of a CSTR in case of our exothermic reactions, to avoid the runaway of the reactions, and whether avoid the runaway of the reactions or to prevent the side products, formation of the side products. So the coolant flow rate is manipulated. I am going to manipulate this coolant flow rate by measuring the temperature of the measuring element T0, temperature of the reaction vessel, so that the temperature of the exit stream T0 of a CSTR that is to be maintained. So temperature of a reactor that is measured and fed to a controller system. Now the temperature of the system that is measured and fed to a controller system, which is going to give me the controlling over the control valve. That is what happens in case of our backward feedback control system. So it manipulates the coolant. There are several resistances in the heat transfer path, that is on the liquid film heat transfer coefficient, then the film coefficient, and on the coolant side, then our resistance because of the metal wall, then the fouling resistances will be there. So all these different resistances contribute to the delay in the response. धीरे धीरे रिस्पॉन्ड करती है सिस्टम because of all these resistances, and as a result my temperature may shoot up drastically. So to take a long time for changes in the coolant flow rate to bring about a change in the reactor temperature and may result in the runaway reactions or increase in the temperature, for that the cascade loops they have been used. Cascade control systems have to be used to manipulate the variables. In this case, one manipulated variable and more than one measured variable that is there. Manipulated variable is only one, however, more than one measured variable that is there. And inner and outer loops that is provided in this case. The outer loop that is called a master or a primary controller and the inner loop that is called a slave or a secondary controller. And the controller output of this master controller is the set point for the inner control loop. So one set point that is provided for the master controller, this master controller generates a new set point for the slave controller. Slave controller measures the second variable and which takes the action on that secondary variable. Now, in case of our normal feedbackward system, our figure is like this: measurement, comparator, controller, control valve. Now, in addition to this, we are providing a slave controller also. Now, this slave controller is obtaining a response from this flow meter also. So, this is my control variable. This is my control variable C. This is a main thing I want to control, and that is why it is called a master controller. And the second one is a slave controller. Till now we have not measured this flow rate which is going inside the vessel, inside the jacket. All the two systems, feed forward, feed backward, we have not measured the coolant flow rate. We have measured this temperature, we have measured this temperature, but we have not measured this flow rate. This flow rate also plays an important role. And in this case, cascade loop, we are measuring this flow rate and making it a slave controller, that is a secondary controller. So this secondary controller will have the set point obtained from this master controller. This master controller will give the set point to this slave controller. And this slave controller, what it again takes, it measures the flow, it receives the feedback from the measurement, flow measurement. So now putting this in case of a block diagram. So this is my reaction temperature that is to be maintained, for which I am provided the set point. Then it goes to a controller, comparator. It goes to a comparator. After comparator, there is a master controller. After comparator, there is a master controller. Then there is a again second comparator that is available. So second comparator that is available, and there is a slave controller, and a control valve that is there. So control valve is there, and after measurement of this flow rate, it gives a feedback to this slave controller, comparator of slave controller. So this feedback is obtained from the comparator of a slave controller. Then the whole system that is going into a jacket. This secondary system is going into the jacket. So it is what? These parameters, that is a slave controller, valve, and this measurement, that makes a secondary loop. So there is a one loop, and the main loop is this outside loop that goes to a jacket. There is a jacket, and a process is available for this, the process that is available. And this can be the another load variable that is shown here, the temperature. In case of a feed forward control, we can manipulate or we can measure this and can apply the feed forward control system also. So this outlet temperature that is measured, and it is going to sense with the thermometer, and that goes to a controller comparator. So this is my outer loop. That is why we observe in the block diagram, there are different loops inside loop that is available, and that is because of either because of this cascading effect or because of the feed forward effect also. So basically feed backward, but as we are making the systems more and more robust, but they becomes more and more complicated and becomes difficult for processing also. So one has to optimize on the parameters which are of more concern and take a proper decision based on that. Now another example, that is a furnace temperature, cascade control of a temperature in case of a furnace. So furnace, oil that is being heated inside a furnace, inside that furnace fuel and air, fuel that is burnt, so the temperature will be increased, and this oil that will get heated. So the outlet temperature of the oil that is measured, which is going to give you a signal or feed back to a controller, and the controller takes an action depending on the temperature, measured temperature, and gives a signal to the control valve for the entry of a fluid, for the entry of a fuel. That means if the temperature of this is increased, I have to reduce this fuel flow rate. Now, in case of a cascade control system, I am measuring the flow rate of the fuel which is entering inside this furnace. And if I measure the inlet temperature of this oil which is entering, then I am providing the feed forward control system. So what is being measured and how that loop is connected, based on that we will have the feedback, feed forward, cascade control system. Then similarly, we can have the examples of the bottom of a distillation column, where we are going to maintain the bottom temperature of a distillation column. That is why it becomes a master controller. And the secondary controller or the slave controller, that is what the heating fluid, measuring the flow rate of a heating fluid. Similarly, in case of a heat exchanger also, the master controller is the outlet temperature of the process fluid. Then that gives a signal, or that generates a set point, which is the set point for the slave controller, where the slave controller measures the flow rate or gets the feedback from the measured flow rate and generates the manipulated variable, which is going to give the signal or command to the control valve. Now next is a ratio controller. It is a special case for the feedback control system. So feedback control system, initially we are measuring the temperature or the flow rate of something. In case of a feed forward control system, we are measuring the temperature or the flow rate for the fluid which is entering into the system. Now we will see a system where the propane that is burned into the furnace, and to burn this propane you require air. So for example, we need 150 kgs of oxygen for say 40 kgs of propane to burn. A certain ratio that is there. So based on this stoichiometric calculation, we will decide a certain ratio, how much amount of the air that is required to completely burn this propane. So primary thing is the propane which is available with me, because to maintain the outlet temperature from the furnace, I have to measure this propane. So propane is the main concern, and to burn this propane, how much amount of the air that is required, that is manipulated. So I am going to take stoichiometrically the amount of the air required to burn the desired amount of the propane. This can be calculated theoretically with certain excess percentage also we can take into account, and provide this value of K for that. So K is a factor, multiplication factor. So as I am measuring the propane flow rate, and I am going to provide a K factor, which is a ratio factor, to burn this much amount of the propane, I require this much amount of air. So that is a ratio which is being provided, and for that I am measuring the flow rate of the propane, and with this ratio controller kitna chahiye? In this case of propane to oxygen, you require 23.81 moles of air, moles of oxygen, sorry. So based on that, I am going to adjust the flow rate of the air which is entering. So I am going to manipulate this flow rate of the air which is entering into the furnace. Now in case of a neutralization reactions, that is acid and alkali that is there. the acidic media is of main concern. So I am going to measure the flow rate of this acidic media. Then based on my ratio, I am going say 2, 1:2. 1 mole of the acid requires the 2 moles of the alkali. So the ratio that has been provided, and I am measuring this flow rate of the alkali which is entering into the system, and accordingly the controller that will take the action for the fluid which is going into the vessel. And for that, this ratio controller that will have a block diagram, that is the K factor which is available as the ratio. So this flow rate that is to be measured, the K factor that is available, then the controller that is available, and this controller will have been provided. This controller controls this control valve, and there is a measurement system which is available here, which is going to give you the feedback system. So this is related to the ratio controller. Then there is a selective control system. In this selective control system, one manipulated variable and several measured variables are there. One manipulated variable and there are several measured variables, and these several measured variables will take a collective decision to manage this manipulated variable. You can look at this figure. This is a cross that is shown as a reactor, where the reactant that is entering into the reactor from one end, and the products which are going out from the another end. So this is my reactor, and this reactor that is covered with a jacket. So this is my jacket, and in this case I am measuring the temperature at different points inside this reaction system. These are all my thermocouples. That is, the multiplexer is used for that purpose. From these several measurements of a control system, now system determines the actual value to be used for this control purpose. So all these different temperatures that is used to control this outlet temperature, that is the outlet product temperature. So this is the selective control action or selective control systems that is there.